identify the basic forms of data movement in a shift register. Basically, you're moving binary data from one register to the other. We explain how serial in, out, serial in, parallel out, parallel in, serial out, parallel in, parallel out shift registers operate. Describe how a bidirectional shift register operates. Determine the sequence of a Johnson counter. A Johnson counter is a special type of counter. Instead of a counter to produce a specified sequence, construct a ring counter from a shift register. We use a shift register as a time delay device. We use a shift register to implement serial to parallel data conversion. We implement a basic shift register control keyboard encoder. So basically, your computer keyboard, each one of the symbols is associated with the binary code that is recorded or stored in a shift register. We interpret the ANSI IEEE standard shift registers with dependency notation. In other words, those are ICs with certain notations. We then talk about shift registers used in a system application. Okay, and so we're basically not going to go through all of these plus, so you know that we actually hone into specific areas of knowledge here. And so we're not going to basically cover everything that is outlined in the objectives, but that gives you an overall idea of what to expect in the chapter. Okay. We then talk about terms and terminology referring to shift registers. So every other chapter, you actually learn new terms and terminologies. In other words, you are able to speak the academic language of the specific subject. So we talk about registers, stage, shift, load, bidirectional. So here we're going to basically cover 4 of the main shift registers, which you can see here in the introduction. It's a serial in, serial out shift register, the serial in, parallel out shift register, a parallel in, serial out shift register, and a parallel in, parallel out shift register. Okay, the serial in, serial out shift register. There's the internal architecture of it. So we can use basically four D-type shift registers, right? Serial data goes into the D input, and serial data comes out of the Q3 output of the last flip-flop. So 4 flip-flops, flip-flop naught, 1 flip-flop, 2 flip-flop, 3, right? And you can see then all of the flip-flops are simultaneously clocked at the same time with a common clock pulse. Okay, so you can see Q3 is a serial data output, and not Q3 is the inverted data output, right? But in serial. In this example, we show the states of a 5-bit register with the specified data input and clock waveforms. We assume that the register is initially cleared. That means all zeros. Right? You can see on the data input there, you got 1, 1, 0, 1, 0. Okay, that's on the data input. At the occurrence of the clock pulse on the positive going edge, right? After 5 clock pulses, that data will be appearing on the outputs of each one of those Q outputs from Q0, Q1, Q2, Q3, Q4. Okay, so the data input is 1, 1, 0, 1, 0. And after 5 clock pulse, you can see on the output, you got 0, 1, 0, 1, 1. Right? The data has to be stored into those 5 D-type flip-flops after 5 clock pulses. So that's parallel serial in, serial out. So the narrative down there says that the first data bit is entered into the register on the first clock pulse and then shifted from left to right, and the remaining bits are entered and shifted. The register contains Q0, Q4, Q3, Q2, Q1, Q0, which is equal to 1, 1, 0, 1, 0 after 5 clock pulse. It's important to note the sequence of the output in terms of the bits that you're going to get at the output as well. So after 5 clock pulse, that's what happens. There's a logic symbol for an 8-bit serial in, serial out shift register. Okay, so data in, and the clock inputs there, and Q7 is the output. So you got from Q0 to Q7 that forms an 8-bit serial in, serial out shift register. That's basically the logic symbol for such a shift register. The next one shows we talk about is the serial in parallel out shift register. So you can see there by the schematics, you got 4 D-type flip-flops. Each flip-flop is clocked by common clock pulse. Data is input into the first flip-flop, right? And so each successive flip-flop has Q0, Q1, Q2, Q0, Q1, Q2, Q3 output, and the output is in parallel. Okay, so the data is input serially into the flip-flop, and each successive stage, the data is clocked from one flip-flop to the next. But to get the output in parallel, you just simply tap off the output of the 4 flip-flops, as you can see there. Okay, that's the logic symbol for that serial in parallel out shift register. You can see the data input is in the D, and the 4 outputs are Q0, Q1, Q2, Q3, as indicated by the logic symbol. The next one is an example. It shows the state of a 4-bit register for data input and clock waveforms in the above figure. The registers are initially all ones, and the data in is 0, 1, 1, 0, and the occurrence of the positive edge of the clock pulse. You can see the output from Q0, Q1, Q2, Q3 appearing on the output of each flip-flop. Okay, so this is an internal architecture of the 74HC1648 bit serial in parallel out shift register. With 8 bits of information there, for you got 8 D-type flip-flops in there. You got SR flip-flops there, sorry. So it's basically a little bit constructed using differently constructed from a D-type flip-flop, but you can use an SR flip-flop to gain the same application or same results. In other words, a serial in parallel out shift register. But that's basically an internal architecture. You can go to an IC shop, purchase this IC, a 74HC164, right? It will be an 8-bit serial in parallel out shift register. In this case, we are using SR flip-flops. So this is the logic symbol for it. And here is the waveform diagrams. Okay, let's not get too complicated about that. That should be fine. Okay, the next one is the parallel in serial out shift registers. Okay, so what we have here is 4 D-type flip-flops, and each one of them are clocked by a common clock pulse, and the data is out there in serial. Okay, so your inputs are D0, D1, D2, D3 going into gates 1, 2, 1, 2, 3, and 4. Gates 1, 2, 3, and 4. And so you have a shift load input on the left. Okay, and the shift load helps us to move each one of the inputs in parallel in and serially out, shifting it serially out. Okay, so basically, when the shift load is at a certain level, the gates G1, G2, and G1, G2, G3, G4 are clocked, right? Pushing the data into the OR gate, right? And when the shift load is at the other level, then it actually clocks it from one stage to the next serially out of the 4 flip-flops. So it's called parallel in serial out shift register. Parallel meaning 4 bits of data D0, D1, D2, D3 is presented at the input, and by the shift load activity, we can then clock all of that serially out. Right? And there's the logic symbol. Okay, so there's the explanation of what to expect in this type of a flip-flop. So you see that when the shift load is low, gates 1 through 4 is enabled, allowing each bit to be applied to the D input of the respective flip-flops. When a clock pulse is applied, the flip-flop with D equal to 1 will set, and those with D equal to 0 will reset, thereby storing all 4 bits simultaneously. So you got 4 bits coming in parallel. When the shift load is low, all 4 gates G1 to G4 are enabled, and that means all 4 bits in parallel are stored into those G-type flip-flops. Right? That's the first stage. When shift load is high, gates G1 through G4 and gates G5 to G7 are enabled, allowing data bits to shift from one stage to the next. The OR gates allow either the normal shifting operation or the parallel data entry operation, depending on which AND gates are enabled by the level on the shift load input. Notice that flip-flop 0 has a single AND to disable the parallel input, D0. It does not require an AND or arrangement because there are no serial data in. Okay, so there's an example here. Show the data output waveform for a 4-bit register with parallel input data, and the clock and shift load waveforms given in the figure, right? So those are the 4 parallel data there, 1, 0, 1, 0, 1, 0. Michael, I'm in class, I'll call you back just now. Okay, show the data outputs for a 4-bit register with the parallel input data, and the clock and shift load waveforms are given in the figure. So that's data. The parallel data is 1 0 1 0, and your shift load function is there. Okay, so that's your input there, and there's your clock input there, and that's your data output. So basically, you got the parallel data coming in at the occurrence of the clock pulse together with the shift load functionality. Then that data is then clocked out in serial on the output. Okay, so on clock pulse 1, the parallel data 1 0 1 0 are loaded into the register, making Q a 0. On clock pulse 2, the 1 from Q2 is shifted onto Q23. On clock pulse 3, the 0 is shifted onto Q3. And on clock pulse 4, the last data bit is shifted onto Q3. And on clock pulse 5, all data bits have been shifted out and only ones remain in the registers, assuming the D input remains a 1. Okay, so the 74HC1658-bit parallel shift register, there's it there. Okay, so this is the internal architecture of a specific IC. So it's parallel load shift register. Okay, so parallel in, serial out. That's the internal architecture of such an IC, logic symbol. And this is the waveform diagram, timing diagram. Okay, so class, this can I just go and get some water and come? I will just let me get away from the computer a little bit, 2 minutes. So this is parallel in, parallel out shift register. I'll come back to this soon. Okay, class, I'm back. Right. So the next one we're talking about is a parallel in, parallel out shift register. And you can see by the architecture what we have here. Right. The schematic diagram shows us 4D type flip-flops. Okay, you got a common clock pulse clocking all 4 flip-flops at the same time simultaneously. Your parallel data is D0, D1, D2, D3. And the parallel data outputs are Q0, Q1, Q2, Q3. So its data is going into parallel into this set of registers or flip-flops, and data is being clocked out in parallel at the same time as well. Parallel in, parallel out shift register, right? And there's a 74HC195 IC that would carry out such a function. See that you got parallel data going in and parallel data coming out, okay? So there's a basic explanation here down, okay? So the 74HC195 can be used for a parallel in, parallel out operation. Because it also has a serial input, it can be used for a serial in, serial out operation. Okay, so some of these ICs are quite versatile, right? In this case, you can see it can be used as a parallel in, parallel out, and serial in, serial out operation. It can be used for parallel in, serial out operation by using Q3 as the output. A typical logic block diagram is shown above. When the shift load input is low, the data on the parallel inputs are entered synchronously on the positive transition of the clock. When shift load is high, stored data will be shifted right, that means Q0 to Q3 synchronously with the clock. Inputs J and K are serial data inputs to the first stage of the registers. Q0, Q3 can be used for serial output data. The active low clear input is synchronous. Okay, so we don't have to go too much into detail of that IC, but you can see these some of the ICs that are presented are quite versatile, and they can be used for multi-purposes, multi-functions. The next one is a bidirectional shift register. In other words, you can shift left and you can shift right. Right? You get data coming into, see, in this case here, serial data is coming into gate 1, and by the arrangements of these gates onto the inputs of the flip-flops, right, you can shift data either left or right. And you got basically 4 D-type flip-flops. Each one is triggered by a common clock pulse. Okay, and you got a shift left, shift right functionality by the arrangements of those gates. Okay, you can see the NOT gate, that's quite instrumental in that. And so by actually making the shift left, shift right at a certain level, we're either going to shift to the right or to the left. And by the combination of those gates, you got gates number G1, G3, G2, G3, G4, and then G5, G6, G7, G8. And you've got all gates that are summing up those 2 AND gates, okay? And let's look at the example down there. So determine the state of the shift register of the above figure after each clock pulse for the given right-left control input waveform. Assume that Q0 is equal to 1, Q1 is 1, Q2 is 0, and Q3 is 1, and that the serial data input line is low. Okay, so basically what we have here is a right-left waveform. Okay, one is when it's right, it's high, and when it's left, it's low. And the occurrence of the clock pulse, depending on what the shift left, shift right is, data is either going to be shifted left or shifted right. Okay, so the input to this to the flip-flops is basically 1011, and you can see that on the waveform in the bottom. So it's 1, Q0 is 1, Q1 is 1, Q2 is not, Q3 is 1. So the first clock pulse, data is shifted to the right. okay? And you can see then the 1101 goes down 110, okay? And then and obviously on the top it will be 0, right? If you shift that again further to the right, the next clock pulse, then you got the 11 is being shifted again, so you got 00 on top, and you got 11, right? And the third one also does the very same thing. Okay, this first, second, third one is 0110. Okay, so in other words, so we're shifting further to the right. And the next clock pulse, we're shifting to the left, right? So the same set of data is actually going to the left, and the next one is also to the left, and the next one is all to the left, the 3 there. Then on the right pulse, it shifts to the right again, and the next right pulse, it shifts to the right, and then the last one, it shows shifting to the left. So those 4 bits of data is actually going left, right, left, right. That's what we're doing there. It's bidirectional, right? You need not boggle your head too much about that arrangement. Okay, so that's a certain IC there. We don't want to do much about that. Okay. The next one is shift register counters. A shift register counter is basically a shift register with the serial output connected back to the serial input to produce a special sequence or specified sequence. These devices are often classified as counters because they exhibit a specified sequence of states. 2 of the most common types of shift registers counters are the Johnson counter and the ring counter. And that's what this section deals about, the Johnson counter and the ring counter, right? So it's a special type of sequence that these counters have. Okay, so we discuss how a shift register counter differs from a basic shift register. We explain the operation of a Johnson counter. We specify a Johnson sequence for any number of bits. We explain the operation of a ring counter and determine the sequence of any specific ring counter. Okay, so there's a Johnson counter truth table. Okay, so what we have here is 4 bits of information. Okay, and the occurrence of the clock pulses from 0 to 7. And you can see that each time the clock pulse is applied, right, a 1 is shifted into the Q0, and that successively shifts to the right in that sequence, in that fashion, right? And you can see those ones, the sequence of those ones that are going in there, okay? Okay, so this is a 5-bit Johnson counter, doing very same thing. You can see the arrangement of those ones. Okay, so the Q0 is not, and you got 5 ones and then zeros up until 9. Okay, and so that's a 5-bit Johnson counter there. But what we see here is that you got okay, sorry, here's a 4. No, the schematic diagram is explaining a 4-bit Johnson counter, sorry, and you basically have 4 D-type flip-flops, and the not Q3 output is then applied to the D input to produce such an effect. Okay, and those are the waveform diagrams here. So that's the timing sequence for the 4-bit Johnson counter, and this one is a 5-bit Johnson counter. Okay, so in this schematic diagram, you can see you got 5 bits of information from the Johnson counter, and the not Q output of not Q4 is fed into the D input of flip-flop 0. Okay, and from that waveform diagram, you can see that all the highs are representing the ones, and that according to the truth table forms a similar pattern. The next one describes a ring counter. The ring counter utilizes 1 flip-flop for each state in its sequence. It has the advantage that decoding gates are not required. In the case of a 10-bit ring counter, there is a unique output for each decimal digit. So basically, in this one here, you've got 10 D-type flip-flops, and the Q naught output, the Q output of the last flip-flop is fed into the D input of the first flip-flop. Okay, and you can see that the truth table for such a counter. So what's different from the Johnson counter? You can see that one is being clocked, right? And at any particular time, there's a one represented on the output of each of the flip-flops, right? From Q0 up until Q9 at a specific point of the clock pulse. And that what forms a ring counter. Okay, so here's an example. If a 10-bit ring counter similar to the above figure has the initial state, determine the output waveform for each output. And that's the initial state that's described on top there. And that's the output for each one of those flip-flops. Okay. Okay, shift register applications. Shift registers are found in many types of applications, a few of which are presented in the section, such as use a shift register to generate a time delay, implement a specified ring counter sequence using a 74HC195 shift register, discuss how shift registers are used for serial to parallel conversion of data, and define UART. UART is universal asynchronous receiver and transmitter. Okay, so because there's a whole lot of applications, around using shift registers. Okay, so you can use them in many situations. So there's a simplified block diagram of a serial to parallel converter. Okay. Okay, there's a block diagram utilizing it in a UART, and where microprocessors are involved, and the data is being moved from one point to the other. Okay, so there's a microprocessor system, okay, and data is going into parallel into a universal asynchronous receiver and transmitter, and so data is then converted from parallel into serial. Right? So that's the parallel to serial conversion of data within the microprocessor. Okay, let's look at something else here. Okay, don't look at that. So okay, so here what we have is a keyboard encoder, right, representing all of the positions on a keypad. So you got your alphabets from lowercase to uppercase, your numbering, your symbols, etc., right? And each one of them is associated with a binary code within the computer itself. And so here we basically trying to see how keyboard encoder for each one of those symbols is represented to the specific code, right? And that's stored within the computer itself, right? You can actually read up on that. It's got to do with the ASCII code, right? The American Standard Code for Information Interchange, National Coding System for keyboard usage, okay? So that's the ASCII code, the American Standard Code for Information Interchange. Okay, I think we can skip all of this here. Okay, so the last part then deals with terms of data. So bidirectional means having two directions. The stored data can be shifted right or left. Load means to enter data into a shift register. Register is one or more flip-flops used to store and shift data. So register can be constructed using the flip-flops, the D-type, SR, or JK flip-flops. Right? And shift is to move binary data from one stage to the next within a shift register or other storage devices, or to move binary data into or out of the device. Stage, one storage element in a register. Okay, class, so that's it for this chapter. I will be repeating the same lecture tomorrow morning at 9:15, and we will then be doing it tomorrow afternoon at Tuesday at 4 o'clock and 5:30 for the evening classes, and also on Thursday at 4 p.m. and 5:30 p.m. for the evening classes. For now, that's all. Is there any questions from anybody? Okay, so class, the next thing for me to do is to actually complete setting my test, and one of the things I have to liaise with the bookings department to get the venue booked. Once that is in place, we will conduct the test next week. I will then text you a scope for it, for the test. I suppose that the scope can be given now as well. Concentrate thoroughly on chapter 1, 2, and 3. And basically, you've got to have to know how to do that counter design that we did last week in class, the 6-step design. And if you don't know that, you cannot come and say to me, sir, I want a retest. I specifically expressed to all of you, there is no makeup test. This is one test, the only test, and that's it. And so there's no makeup test. So I've given you everything that you need to know. And please go on to chapter 1 as well and thoroughly know all of that, the 555 timer, the internal architecture, and chapter 2. Chapter 1 also deals with the 3 type of flip-flops, the D-type, the SR, and the JK flip-flops. You need to know how to do the logic symbols, the internal architecture, and the truth tables for those as well, right? And you've got the 555 timers that we spoke about, the monostable and the A-stable. There's a few calculations surrounding that. There's some formulae around that. Please go through those thoroughly and know them for test 1. Okay, but I'll give you a more specific outline on that going forward soon, once I finalize the test. Okay, so let's call it quits now. That's the end of the lecture for today.
Sorry, sir.
Yeah.
So when are you writing the test?
I said to you, once I get the bookings done, I haven't got the bookings done for the venue, so I can't tell you a date. It starts with getting the venue booked first. So once the venue is booked, then only I can tell you what date it is.
Okay, thank you, sir.